let's start with problem 7, which was problem 3 of the 2015 USAMO. So the problem says let S be the set from 1 through n, and then there are 2 to the power of n subsets of S, and each are colored either red or blue. So then Ft is the number of subsets of T that are colored blue, and we want to find the number of colorings that satisfy this equation for all subsets T1 and T2 of S. Yeah, so the main idea of this problem is just casework. So we want to add an additional condition that breaks the structure of this equality, and we find that the most characteristic property that we can use for casework is the color of the empty set phi. So case 1 would be that F phi equals 1. So the color of the empty set phi is blue. So what happens in this case is that if we choose any F1 and F2 that are disjoint, so F1, the intersection of F1 and F2 is the empty set, what we find is that Ft1 and Ft2 is equal to Ft1, T2. So what this tells us is if we take any set and we have its F value, then we can decompose it into two smaller subsets that are disjoint, that partition the set T1, T2. In other words, if we have some set B such that it is B1, B2, all the way to BK, then we can say that FB is equal to F, and then the single element set B1, single element set B2, all the way to FBK. So to briefly introduce some notation to expedite this process, we say that T for some subset T is 1 if T is blue, and 0 if T is red. Then this is just equal to the multiple of C BI plus 1. So it's just the color of the single element subset BI, and then plus 1, and that multiplied gives the value of FB. So now we have the idea to take the subset, take some subset C with elements C1, C2, all the way to CT, where these are the T elements, so that their single element subsets are blue. So these are all the elements such that Ci is blue. So if we look at FC, FC is just equal to phi I equals 1 to T, Ci plus 1, which is 2 to the power of T. But now we notice that the number of subsets of T is 2 to the power of T. So what this means is that every single subset of C must be blue. Every single subset of C must be colored blue. And if we look at Fs, the F value of the entire set from 1 through n, we can see that this is equal to I from 1 through n, C with the single element subset I plus 1. But notice that if Ci is 0, then this is just 1. And if Ci is 1, this is 2. So this is just equal to 2 to the power of T. So Fs and Fc are equal. Now, what this tells us is this. For any subset T, T is colored blue if and only if all its elements are blue. So in other words, T, if we say that T is like T1 through TK, the subset T is colored blue if and only if the single element subsets T1 to TK are all blue. So we know that now that we have constructed a bijection between the colorings and the set such that all the single element subsets are blue. So the number of colorings in this case is the number of ways of choosing this subset C, which contains all the blue elements. And that is just 2 to the power of n. And also we have to add plus 1 here actually, because there's another case where every element is just red. And that obviously satisfies this, because then all of these would be 0. So this is what we got for case 1, which is F phi equals 1. So then case 2 would be Fi equals 0. And what case 2 tells us is that if we take any disjoints T1 and T2, then Ft1, Ft2 equals 0. So one of these must have all of their subsets blue. So now let's take the subset C, that is the smallest subset. That is blue. So that in this case, C wouldn't be empty because the empty set is 0. So if we take any subset, so now let's see this equation Fc, Ft equals Fc. And let's take T such that it is disjoint from C, so then this is 0, then this whole thing is 0, right? And since Ft is not equal to 0, then Fc is 0. My bad. Ft is 0. So any subset that is disjoint from this smallest subset C must have all of its subset red. Now, extending this logic, there's actually a very interesting, how do I say this, like bijection that we can see to the smaller cases in that now we can ignore all the sets that are disjoint from C. What about sets that have an intersection, that have a non-zero intersection with C, but that still have elements over here? So C is so the intersection of C with T is not empty, but at the same time, C is not a subset with T. Then what we find here is that Fc and T must still be 0 because if we say that Fc and T is not 0, this contradicts the minimality condition we added to the definition of subset C. So then here we can also see that Ft must be 0. And so all the subsets that we're interested in are subsets that just contain the smallest subset C. And here we can see that if we consider C to be the null set, this is just a bijection to this Fi equals 1 case with the number of elements being n minus the number of elements of C. So then computing this would be the number of ways of choosing C. And then for the rest of the elements, you would have to sorry, I'm having aneurysm. So this would be the number of ways of choosing this is equal to the number of ways of choosing C, and then sorry, please wait like 2 minutes. I just think this through. All right, so this is just equal to the number of ways of choosing some subset and then coloring the rest randomly, which is just 3 to the power of n. And then we have to exclude the case where C is 5. So 2 to the power of n. And so adding these two, we get the total number of colorings. And right. And to illustrate this point, this is equal to taking, there's this set of n, then you take a subset C and then color the rest, either 1 or 2. But this, if we consider the sets of set C just color 3, this is just equal to coloring all the elements of n, either 1, 2, or 3. So this is just 3 to the power of n. And I'll probably have to re-record that section. Okay. So there's 3 to the power of n minus 2 to the power of n, 2 to the power of n plus 1. So you add these. Thank you. 3 to the power of n plus 1. All right. Oh my God, that was a terrible explanation. Sorry. I'll try better for the next question.
Can you go a little slower?
Yeah. I sorry. Next problem is hopefully a bit more straightforward. Problem 2, which is, so problem 2 is you have n, okay, I'll go slowly, sorry. So you have n pebbles in a vertical column. So you have n pebbles in a vertical column, and the move is essentially if you have a column and a column to its left, and this column is at least 2 higher than this one, then you can move 1 pebble from this column to here. So like just it's on the problem. It's just explanation of the problem. And the question says that if no pebbles can be moved, the configuration is called the final configuration. And for each n, show that no matter what choices are made at each stage, the final configuration is unique, and describe that configuration in terms of n. So there are 2 different solutions for this. There's the 시간 어떻게 되죠?
선생님한테 10분만 좀.
So I'll actually just go through both the official solution and my solution to this problem. So I'll do official first. So what the official solution says is the final configuration, first of all, if you just try out small n, you know that the final configuration is the triangular configuration. Which basically means, like, for example, n equals 10, then this will be 4 in the first column, 3 in the second column, 2 in the third column, and then 1 in the fourth column. So it's like this triangle shape, and it's descending. Another example, n equals 11, then it'd be 4, 3, 2, 1. And then to complete the triangle, we actually add 1 here. So computationally, this would be, so if we let c equals 1 plus 2 plus t plus 1, and then 1 plus 2 plus t, and s equals c minus, it's basically just this, but written in a more formal way. And this would be, this is the number of pebbles in column I. And this is just equal to c minus I if I is less than or equal to c minus s, then c minus I plus 1 if I is larger than c minus s. So how do we prove this? So what we do is we actually add we prove 3 conditions of this construction that forces the final configuration to be this triangular configuration. And those 3 properties are that at any stage P1, P2, so it's the sizes must be in descending order. This should be pretty clear from the moves itself, because we have the condition that the left column must be at least 2 higher than the right one if we are going to do a move. And so that preserves this. It should be clear from the operation given. Second condition is at any stage, okay, this is a long, at any stage, it is impossible to have some I larger than j, such that pi equals pi plus 1, pj equals pj plus 1, and pi plus 1 minus pj is less than or equal to j minus I minus 1. So in other words, if we have column, so we have I plus 1, I that are of equal size, and then this j column, and then j plus 1 column that are of equal size, and this slope between I plus 1 and j cannot be less than or equal to 1, and we're going to prove that now. And the idea is induction on n. So we assume that something like this is possible. And of these possible configurations, we choose the one that has the minimal value j minus I. So here, the implicit assumption is that something like this exists. So for the sake of contradiction, assume something like this exists, and then of these, choose the configuration that minimizes j minus I. And then we look at the first time that these conditions are met. So the first time that there exists some columns I plus 1, j plus 1, and then having this average slope be less than or equal to 1. So if we look at the previous move, since this is the first time that this occurred, the previous move must have generated these columns. So we know that the previous move must either be an I minus 1. So a movement from I minus 1 to I, or a movement from I to I minus 1, I plus 1, same thing, j minus 1, j, or j plus 1. And we just proved that all 6 of these previous moves lead to an inevitable contradiction. So if we say that the previous move was an I minus 1, right? So we moved the pebble from I minus 1 to I to create this state. But this means that in the previous state, the column of I was shorter than the column of I plus 1, which is a contradiction by condition 1. So contradiction by condition 1. If it was an I jump, well, then we moved a pebble from I to I plus 1 to create j. Oh, and so here we need an auxiliary condition, which is that actually if the slope is less than or equal to 1, then actually every single drop from here on out to j must be 1. So every single drop must be, and this is because let's say that we had a drop that was larger than 2. So there's a column in between here with k plus 1, so that this distance is larger than or equal to 2. Then this is a contradiction because the average slope is less than or equal to 1, there must also be a 0 drop. So there must also be some other k prime and k prime plus 1 such that these two columns are equal because the average drop is less than or equal to 1. We need something to balance out this large drop here. And then this is a minimality condition, a minimality contradiction of j minus I, because k prime minus I and j prime minus k are both smaller than j minus I. And also note here that if j is equal to I plus 1, this is a clear contradiction because you can't have 3 columns of equal height at any time. Right, so every single drop must be 1. And if an I drop generated this structure, this means that, so we moved a pebble from I to I plus 1 to generate this, but then I plus 2 is 1 lower than I plus 1. So in the previous move, I plus 1 and I plus 2 must have been equal heights. And that is, again, a minimality contradiction because j minus I plus 1 is smaller than j minus I. So we were able to generate another one of these constructions that violates the minimality condition of j minus I. I'll just do until I plus 1, and then these are pretty redundant. Again, let's say that the previous move was a pebble moved from I plus 1 to I plus 2. This implies that the column I plus 1 was actually higher than column I in the previous move, which is a contradiction of condition 1. And so all of these are impossible. Similar logic, all of these are impossible. So such a j minus I can't exist, and we have proved condition 2 for all constructions. Right. And then condition 3 says at the final configuration, all drops are 1. So all adjacent columns, the right column must be exactly 1 lower than the left one, with at most 1 exception. So there's at most 1 columns such that these two are equal, and then the rest must all be 1 drops where the left column is exactly 1 higher than the one on the right. This actually follows pretty naturally from conditions 2 and 3. So if we have 2 0 drops, that's a violation of condition 2. So we can't have 2 0 drops. And then if we have a drop that's bigger than or equal to 2, we can actually do the operation, so it's not a final configuration. So we now proved condition 3, which says that all drops are 1 with at most 1 exception, which is a 0 drop, and that actually forces the final configuration to be triangular, proving this statement. Any questions?
In condition 2,
Yeah.
can you read again the proof line and
All right.
explain what we assume precisely?
Yeah. So at any stage, it's impossible to have I larger than j, such that like these conditions, right? So for the sake of contradiction, we assume that something like this is actually obtainable. So of the obtainable configurations, there's one that satisfies these properties. So that we have, so let's say that we have a number of these condition violating configuration that we can choose from. And of these, we choose the one that minimizes the value j minus I of the possible ones. And so I kind of, okay, I get why it's confusing. So if we say that j minus I is 1, so okay, so I is bigger than j, so the smallest possible value of j minus I is 1, right? So first of all, if we say that j equals I plus 1, then we will have 3 columns that are same height in the previous, yeah, so we will have 3 columns that are the same height, 3 adjacent columns that are the same height. And again, if you look at the move previous to this, so let's look at the first time something like this occurred. So we have this n column, and we're doing a sequence of moves to create this. And the first time this occurred, then the previous move must have changed one of these 3 columns, or else it wouldn't be the first time it occurred. And then you just do casework, so either I plus 1, I plus 2, and then so the previous move must have either been an I minus 1, I plus 1, or I plus 2 jump. And if you actually just try these out, these are all contradictions. So let's say the previous move was an I minus 1 jump. Then we move the pebble from I minus 1 to I to generate this structure. But then this means that actually column I was shorter than column I plus 1 in the previous move. This is a contradiction by condition 1. Let's say that we again, same thing. If we moved I to I plus 1, this is a contradiction by condition 1, condition 1, condition 1. So this is impossible. So then we know that the minimal value of j minus I is larger than or equal to 2. And then it proceeds in a similar way to this. So we look at the first time something like this was created. And then if we look at the previous jumps, we do casework. Since the previous move must have generated this configuration and must have changed I plus 1, j plus 1 of these 4, which limits the last move to one of these 6 cases. And if we look at each of these 6, they all lead to contradictions. So then condition 2 is proved. Okay. These are a lot more difficult to explain than I thought. Next time I'll bring some more approachable problems. Sorry about that. All right. So the next solution is the one that I found when I first solved this problem. So the fundamental logic of my solution is that, let's say that you have a sequence of moves like I1 jump, I2 jump, and then IK jump. So here, like an I jump means that you move a pebble from column I to I plus 1. And then let's say that you generate a final configuration through these sequence of moves. So my idea was that if you take all the 1 jumps and bring them all up to the front, then if, pardon?
What does a 1 jump mean?
Yeah. So an I jump is moving a pebble from column I to I plus 1. So 1 jump is moving from column 1 to column 2. So if you bring out all the one jumps to the front, so we have this like, okay. So let's bring out all the one jumps to the front. So we just shifted all the one jumps to the beginning and the rest proceeds as in the original order of jumps. Then actually, if you only look at columns 2 through n, this is a valid move order. So I'll explain this. So if you do all the one jumps in the beginning, and then you look at how the pebbles from column 2 are distributed from columns 2 through n, that's another move order that satisfies the condition of the problem with a smaller number of pebbles. I don't know if that makes sense. Yeah. Please feel free to ask questions if this doesn't make sense. And what this motivates us to do is, since we have reduced this problem to a smaller number of pebbles, we can actually use induction on the number of pebbles to prove that the final configuration must be triangular for all n. So we claim that final configuration must be triangular. Oh, and to kind of explain more about the motivation of using an induction, we were able to easily characterize the final configuration. So that means we know exactly what the final configuration looks like, and that partially motivates the usage of induction, because if you can fully characterize the predicted behavior of a sequence, it's much easier to use induction. Like if it was a very abstract object and you don't know how it moves and goes to infinity, then it's pretty much impossible to use induction because you don't know the properties of previous iterations, which makes induction a lot more difficult. So anyways, we were able to fully characterize the final configuration as triangular, which motivates induction. And also this idea of pushing all the one jumps to the front motivates the usage of an induction. So small cases, you just have to try them out. It's just like computation. So this should be clear. And assume satisfied for all n for all n less than or equal to n0 minus 1. And we want to prove that for n, final configuration equals triangular. Okay. So let's say this. So we have column 1. So this is the initial condition. And then, as I said, we're going to move all the one jumps to the front. So let's say that there were L1 one jumps. So then the number of pebbles in column 1 will become n minus L1. And then column 2 will have L1. And then from column 2 onwards, if you only look at this isolated system, it's another sequence of moves that satisfies the problem condition. So actually, by our induction argument, the final configuration must become the triangular configuration with L1 pebbles, except that this shifted one, right? Because we have this one column here. So then the idea here is this. So let's say that like triangular L1 and then 1. Let's say that this denotes the number of columns, the number of pebbles in the first column in the L1 triangular configuration. So the triangular configuration with L1 pebbles. Then because this is another problem satisfying final configuration, we get this inequality that n minus L1 is less than or equal to the number of pebbles in the first column in the L1 triangular plus 1, because this difference must be less than or equal to 1 for it to be a final configuration. And this, in turn, is larger than or equal to, because if this is smaller than this, then we obtain a final configuration where column 1 is shorter than column 2, and that's a contradiction by condition 1 of our previous solution.
For the first time we moved L1 times to create the second column that's L1 of length. By creating the next sequence of moves with L1 only, wouldn't we make the T of first column smaller, much smaller. So the difference between M minus L1 that we have from the beginning and the first column of the triangular formation be more than 2, so we have to move again from column 1.
Right. So if we look at the natural order, so it'll be like column 1 and then column 2. So you move pebbles from column 1 to column 2, and then column 2 moves to column 3. So 2 gets shorter, and then you move again, and then 2 gets shorter, move again, 2 gets shorter. So that's your argument, right? Yeah, right. So this is very inconvenient for us. It's pretty much impossible to analyze this behavior of 1 going to 2 and then 2 going to 3 and 1 going to 2 back again. It's very, very inconvenient. So what we do is we move all these 1 jumps to the beginning. So let's say that in the process going to the final configuration, there are a total of 101 jumps. So in total, throughout the entire sequence of moves, exactly 100 times you move a pebble from column 1 to column 2. So then just in the beginning, just moves 100 pebbles from 1 to 2. And this will probably make a situation where column 2 is taller than column 1. But we don't really care because we're only looking at the isolated system from column 2 onwards. So now column 1 has done its job. We don't care about column 1 now. But looking back at the final configuration, it still must satisfy the properties of final conditions, which gives this inequality. 다음엔 더 너무 복잡한 문제들.
Now because column 1 and the triangle formation has difference that is equal to 1 or less. The next, so from the top of the triangular formation to the next one also has to follow that in an inductional way. What you're saying, right? So that creates.
Okay. Okay. So right. So we do all the 1 jumps in the beginning, right? Yeah. And then we just ignore column 1 for now. We only look at here onwards. So this is a sequence of moves, and the idea is if this whole thing is a final configuration, column 2 onwards must also be a final configuration where a jump is impossible. A final configuration is a configuration where jump is impossible to do. And if it's impossible to do on this whole thing, it's impossible to do from column 2 onwards. So this is a final configuration, right? With L1 pebbles being the initial number of pebbles. So that we use induction on n because we assume that this is satisfied for all less than or equal to n0 minus 1. So then if we only look at here, this from column 2 onwards, the final configuration must be a triangular configuration with L1 pebbles initially. So we see column 2 as the new column 1. We're only looking at this system now. Column 1 has moved all its pebbles to column 2 and has done its job, right? So in the final configuration, this becomes a triangular L1 if we say L1 is the total number of 1 jumps. But so this system so now we add column 1 back to the picture, and column 1 must satisfy this inequality. So TL1 here is the number of pebbles in the first column of the triangular L1 configuration. And then because this is a final configuration, this must be satisfied. Hopefully this inequality is clear from the properties of the problem that we previously discussed.
One question. Out of the 1, 2, 3 in number 2, by the word satisfied, what do you mean? Like what condition is it satisfied?
So the condition is that the final configuration is triangular.
So n small, and it satisfies for all numbers less than or equal to n minus 1, and then you see that it's triangular. So
right. So if n is small, so like n equals 1, 2, 3, 4, like you can just try it out with like these, right? So you can prove that the final configuration is triangular for these small numbers, and then we use the induction. So we assume that this condition is satisfied. So for some n naught minus 1, and then we prove that's true for n naught. And then by induction, we can say that this is true for actually all positive integers n.
So we're going all that down.
Yeah. We're doing normal induction. Yeah, okay.
can't jump from a short.
Right.
Well, it doesn't matter. You're gonna do all the jumps.
So is it just a configurous feature?
Okay. Okay, I'll just explain this from okay. So we have a sequence of jumps. You have I1, I2, and all the way to IK, right? So we have this sequence of jumps, and some of these there are going to be like 1 jumps, 2 jumps, 3 jumps in the sequence, and it goes toward the final configuration. The idea is that the order of jumps doesn't affect the final configuration. Like if I have 3 and then like 0, 0, and I do a 1 jump and then 2 jump, right? 1 jump, 1 moves here, and then 2 jumps, so 1 moves here. I know this violates the problem, but like this is an example. So the final configuration would then be 2, 0, 1, right? If I do a 2 jump and then a 1 jump, then this will be -1, 1, and then I do a 1 jump, which is 2, 0, 1. The order of moves doesn't matter. The final configuration is still the same even if I change the order of moves. And I know that in the intermediate sequence, there might be violations. There might be a column with like -1 pebbles, which doesn't make sense. But it violates the problem condition, but since the order doesn't matter, the final result must still be a problem-satisfying final configuration. And that's the idea of this argument. So we're just changing the orders. We're not changing any jumps or whatever, right? So the final configuration is still the same. And then, so there are no 1 jumps here. All the moves here are interactions between columns 2 and beyond. So we're just looking at this isolated system, and then from column 2 and beyond, it must be triangular by our inductive assumption. Okay. So we obtained this inequality. And if you look at how these 3 numbers change as L1 changes, this is strictly decreasing. Right? If L1 goes up by 1, this goes down by 1. This is weakly increasing. The number of pebbles in column 1 weakly increases as the total number of pebbles increases. Right. So as L1 increases, these two are weakly increasing. This is strictly decreasing. So at most, there are 2 valid L1 values that satisfy this inequality. So case 1, only one L1 satisfies this. Well, then this is clear then, because there's only one L1 value. There's only one valid sequence of moves that leads to the final configuration. So there must only be one unique final configuration, which must be the triangular configuration. So we are done here. Well, what if there are 2 valid L1s? Well, this is pretty difficult to visualize, but let's say that there are 2 different possible L1 values. So this means that, so let's say that the 2 valid L1s are like L1 and then L1 plus 1. Both of these satisfy this inequality over here. So then we would have, in the L1 case, this would be n minus L1. Then this would be the triangular configuration with L1 pebbles. But not now for the L1 plus 1 case, this would be n minus L1 minus 1. And then this would be the triangular configuration for L1 plus 1 pebbles. And both of these satisfy this inequality, but this is strictly decreasing. So this means that here, the first column of triangular L1 has exactly 1 less pebble than n minus L1, while here these two have equal number of pebbles. So first column of L1 has n minus L1 minus 1 pebbles, right? So the first column of triangular L1 plus 1 has an equal number of pebbles to the first column of triangular L1 at n minus L1 minus 1. Okay. So here, now we're going to add column 1 back to the picture. So column 1 and column 2 at the final configuration have an equal number of pebbles. What does this mean? Well, this means that the final one jump occurs after final two jump. Because the one jumps fix the column 1 at this value, which is equal to the number of pebbles in column 2. But at any moment, the number of pebbles of column 1 must be greater than or equal to the number of pebbles in column 2, which gives this argument. Final one jump occurs after the final two jump. So we have the sequence, and then the final one jump, and we will have more jumps over here. But there are no two jumps here. So this is the final one jump. There are no two jumps. There are only going to be 3, 4, all the way to n jumps here, right? So now we can actually just move this one jump all the way to the right. And this time, it's not a problem violating change of order. It still satisfies all the problem conditions. Because if we have two jumps that are completely isolated, their order doesn't matter. So we have sequence, and then this last, and then we move this one jump over here. And our idea is this. Now, let's look at this isolated system. So this time, so we move the last one jump over here. So here, the total number of one jumps is L1 minus 1. And we still reach this final configuration. All right, and then this is a clear contradiction because the number of pebbles in columns 2 all the way to n, the number of pebbles in columns 3 all the way to n are solely determined by here. So the number of pebbles in columns 3 all the way to n are equal in triangular L1 minus 1 and triangular L1 plus 1. And what this means is that when we're adding numbers to the initial number of pebbles in this triangular value, the only value affected must be column 2. So the columns actually, I apologize. This should be L1. Because we're looking at this case where there are L1 plus 1 jumps. So this would be triangular L1, right? So the columns 3 through n are identical in triangular L1 and triangular L1 plus 1, right? So these two are identical. So we added one more pebble to our system, but columns 3 through n are identical. So what does this mean? Well, this plus 1 should go to, or is forced to go to column 2. Well, here we said that the first column of triangular L1 is forced to be equal to the first column of triangular L1 plus 1. But here this argument says that actually first column of triangular L1 plus 1 is strictly greater than the first column of triangular L1. This is a contradiction. And so it's impossible to have two valid L1s. There must only be one valid L1, which proves the uniqueness of the final configuration. Questions? It's fine if you can ask me to repeat the whole thing. I'm fine with it. Just like if you have anything that's confusing here, please.
The configuration in terms of n would be
Pardon?
because the problem is describe that configuration.
Yeah, so it'll be the triangular configuration. Right. Should I write down the equation for you again? Triangular configuration, it's very annoying, but it's right. So we have 1 plus c minus 1 and 1 plus c, and then let s be n minus. And the final configuration can be described as pi is c minus I for I less than or equal to c minus s, and the c minus I plus 1 if I is larger than c minus s. We prove the uniqueness of configuration. It's forced to be the final configuration. And it's 11:50. Okay.